Let's get started. Welcome everyone to the next iteration of tinyML Talks. Sponsors are Edge Impulse. They provide a developer platform to take machine learning from design to deployment at scale. Visit edgeimpulse.com for a free trial. I'd like to also make an announcement about an upcoming event, joint webinar with the IEEE Solid State Circuit Society and tinyML, the intersection of Solid State Circuit Society and AI, a tale of two journeys. Professor Boris Merman and Professor Vivian Z will be speaking on Tuesday, May 26th, 8 a.m. Pacific time. Also, our next tinyML talks on Thursday, May 28th will be by Laszlo Kindrat and Michelle Magno. Two great talks coming up. Again, same time, 8 a.m. Pacific on May 28th. Please contact talks@tinyml.org if you're interested in presenting in an upcoming tinyML talk. So the first talk for today is going to be about embedded computer vision hardware through the eyes of AR/VR by Hans Reyserhove from Facebook. Hans Reyserhove is a postdoctoral research scientist at Facebook Reality Labs. His research focuses on intelligent vision systems and sensing technologies for augmented and virtual reality. He holds a PhD from University of Leuven, Belgium, focused on design of energy-efficient microcontroller systems and better than worst-case silicon systems. He has an MS degree focused on CMOS image sensors with pixel-level A to D conversion for extreme parallelism. His main interests lie in design, prototyping, and optimization of silicon systems, including image sensors, hardware accelerators, and computer vision applications. And here we go. Take it away, Hans.
Thank you, Ravi. So like you said, I'd be happy today to shed some light on how we are thinking about embedded computer vision hardware for AR/VR in our team at Facebook Reality Labs. And as we all know, and that's why we're here today, computer vision nowadays is heavily ML focused. So I hope it makes it of interest to you all as well. First of all, I do have to acknowledge my fellow researchers at the lab, the management, the group, and the entire company for contributing to all of the things I'll be sharing with you today. I would also like to thank the ML community, the tinyML community, for hosting me in this webcast. So at OC6, our developer conference, the head of Facebook VR announced that Facebook is building AR glasses. Now, what does that mean? AR is something that we've all seen in science fiction movies, but it's quite hard to imagine the day-to-day impact. To be honest, before I got at our lab, I had barely seen the tip of the iceberg. Like most of us, I was more accustomed to this idea of Internet of Things, or IoT. Things in our environment that are connected, smart, and always on, but therefore also huge constraints on power, form factor, and performance. Now, I would say that AR can solve all of the consumer-related problems in this design space simply by making everything an inside-out problem. The fact that you have a personalized display that interacts with literally everything in the world makes it almost all the other devices become irrelevant. AR can be a personal assistant. It can sense your environment. It gives you superpowers, and it enables social interaction across distance. Now, the reason that AR is special in this regard is because it has a much wider range of input and output modalities. That is if you compare it to a normal personal computer or a smartphone. So when this technology is realized, it will come much closer to the experiences that we have as humans going about our day-to-day life. Cool, that's the AR promo talk. At the end of the day, it's still a connected, smart, always-on device with huge constraints on power, form factor, and performance. So obviously, there are lots of crucial scientific fields where technology has to advance in order to make this happen. Today, I'll focus mostly on computer vision and the system stack that we need to enable. Everyone who's interested in more of this, I encourage you to take a look at the Oculus Connect keynote talks. They're on YouTube. And especially the ones from our chief scientist, Michael Abrash. They are a lot more elaborate than what I have time here to share. The biggest technology challenge is definitely where it all comes together, the glasses on your head. Wearing something on your head becomes quite intrusive and heavy fast. So to be comfortable, it has to be lightweight. Secondly, minimal power. Power is everything. And power is not just a battery or even a form factor constraint. Essentially, all the power is dissipated as heat. So this means you have to consider the heat dissipating in a form factor like glasses. It also means you can't simply double the energy density of the battery and get away with it, because you will be burning people's faces. Finally, there's no point in building something that people won't use, so the form factor will matter. As a point of reference, I have my sunglasses here, which are about 30 grams. I also have this SparkFun Edge device that we talked about a few weeks back, which is also about 30 grams. And then I have this Oculus Quest headset, which weighs in about 600 grams. Obviously, the golden mark is somewhere in the middle, but I think we can summarize all of these considerations in one word: tiny. Like I said, I will be talking about computer vision and hardware, but in doing that, there's no way around image sensor hardware. It's pretty clear that they are the fundamental sensing technologies that enable a lot of the AR use cases. So what I'll do next is briefly walk through the different properties of those sensors. First of all, the Oculus Quest that I just showed today. Anyone who's ever seen a Quest up close can tell it has 4 cameras. And to be clear, these are monochrome cameras. So in any case, it will never be used to take nice pictures of your environment. They essentially enable the fundamental tracking technology in the headset. They also perform the tracking of your controllers, which are handheld. And nowadays, they even track your hands themselves. Finally, they also enable see-through, which allows you to navigate your real living room or your real space without taking the headset off. They have a medium resolution, about VGA resolution. And in AR, VR, they are what I would qualify as always on. So they operate whenever the device is on, whenever it's on your head. So the operation of that system is as follows. First of all, you need to do an exposure of the camera. You need to collect light, which essentially forms your image. Secondly, what I would call inference is the actual computer vision part, running your algorithms, either algorithmic computer vision or learned computer vision. You need to communicate those results through the system stack, and you put your system to sleep. And we have to realize that this sleep portion is there because with nowadays technology, including the exposure time at a normal frame rate, let's say 50 frames per second, the full frame period is about 20 milliseconds. So it is fairly feasible to do all of this within those 20 milliseconds and still put your system to sleep, which means that what we call always on is actually still off for 50% of the time. Well, when we look at this always on story, we could make the observation that we actually have a lot of slack in this system, calling this sleep. But obviously there's also latency. It's an important aspect in the real-time operation of an interactive device. And something like exposure time, which is inherent to the camera, is a big part of that latency. So when we want to think about optimizing this system, it's important to keep that in mind. An interesting story there is about eye tracking and latency. Hololens, which is an AR device that's currently on the market, has this functionality and it supports automatic scrolling. So the story goes that the latency in this case is actually better than the human brain, in the sense that you typically don't realize that you have reached the end of the page that you're reading, but because your brain hasn't processed that information yet, but your eye is already moving on, and therefore the device can see this and scroll without you realizing it. Before we move on, I want to touch on a couple of sensor specs. The goal is to come to a global shutter, low light sensitive, high dynamic range, and high frame rate camera. Sorry. So first of all, global shutter. We typically use global shutters which capture your scene instantaneously. Especially important in something like AR, VR, which has a first-person view of your reality, which means that it includes head motion, which can be fairly fast. Second, low light. We want to be able to take pictures in relatively dark environments because you will want to use the device in those environments as well. Third, high dynamic range. If you look at a typical illumination range from, let's say, moonlight to direct sunlight, that's a ratio of 10 million to 1, so 140 dBs. Now, you would say I can't see the moon and the sun in one picture, but if you think about a car headlight and a pedestrian on the sidewalk, that ratio comes pretty close. So if you want your computer vision system to support those things, similar to self-driving cars, you should enable this functionality. And third, frame rate. Obviously, the scene that you want to capture and the events that you want to capture are proportional to how effectively you sample them, which is essentially your frame rate. Now, you could say that all smartphones today in our pocket can do most of these things. They have low light sensitivity, they have high dynamic range, they have a good frame rate. But I would say that that is computational imaging. It's not always on. And the algorithms that run in the background to enable that are actually heavier of a workload than the always on use cases that we are trying to enable using our cameras and AR/VR. Finally, a word about sensor resolution. Here I looked at a few typical objects, such as a font on a book, street signs, windows, and storefronts. And I assumed I need to see those objects at least 32 pixel scale to be able to infer them using computer vision. Well, you can then compare a 1 megapixel, a 5 megapixel, a 12 megapixel camera, which gives you those pixels then at what distance. And it turns out it's actually quite a challenge to see these relatively small objects at a relatively far distance. Now, this 32 pixel requirement is a bit of a conservative side, and it's obviously also affected by what lens you use, but you want high field of view, and this will become a problem when you bring everything together. Finally, we have to recognize that these are cutting-edge CMOS technology devices, so there will be a bunch of non-idealities. Traditionally, these effects are masked by an ISP or an image signal processor or some low-level correction. And we do have to recognize that we see a lot of data sets out there that are using nice pictures that come from high-quality cameras that have built-in correction. There is some indication that computer vision, especially machine learned, can train tolerance for these things, but I wouldn't go as far as saying that we can just ignore them altogether. The summary here, in my opinion, is that the sensor hardware is a fundamental part of this computer vision stack, and any compromises that you make at the hardware level should be in line with your end-to-end device use case for the entire device lifetime. Now, moving on to more of the application domain of embedded computer vision hardware. The most fundamental problem that we solve is positional tracking. That is because it enables the illusion of world-locked content that you move through in virtual or in augmented reality. So it's not just about the 3 degree of freedom pose, so what your head orientation is, but also where exactly your head is in the room, the 6 degree of freedom pose. So on top of that, you need an input interface. Recently, we've moved from controllers to hands. And last time I checked, hands don't have IMUs or accelerometers. So this is a pure computer vision problem. Now, the goal for AR is to overlap virtual objects with real objects. So ideally, you should also be able to localize and segment every single object in the field of view. Finally, eyes are a very important aspect for a bunch of reasons. I'm not going to go into detail here, but in a nutshell, eye tracking is a go, no-go use case for advanced VR and AR. Now, all these problems are quite ML focused. A typical classification network could achieve most of these tasks. That is if it's being trained to find bounding boxes of hands, for example. You also need to localize the objects in your scene to enable occlusion, like I said, deciding to render a virtual object before or behind a real object. And that is still a difficult problem, locating everything in your scene. Another approach there would be that you segment your scene for different occlusion planes, which is essentially depth, which brings you closer to the type of UNet architectures. Now, if we look closer at the memory pattern requirements that we have here, what I did is took a typical set of classification networks from VGG to MobileNet and ResNet, and I've simply plotted their input activations, their coefficient memory, and their output activations at any given point in time during inference. So essentially the memory footprint that you need to compute a single layer at that point. And in classification layers, you see this typical trend where the number of channels doubles, the activation size halve in each dimension, which means that your activations actually halve and your coefficients double. So with some fine tuning, you could argue that your memory footprint during inference remains relatively constant. Now, segmentation networks, on the other hand, have quite a different pattern because there's a lot of skip connections in something like a UNet. Here I took a UNet with a ResNet 18 and a ResNet 50 backbone. These activations persist over a lot more layers, which counteracts the shrink in activation size. So it's a bit more challenging to figure out these memory footprints. Now, to enable these types of networks in custom hardware, you can use a full box of tricks that researchers have come up with over the last decade. Whether the end result will meet your footprint is a function of a lot of parameters. And overall, I'm happy that there's something like the tinyML community that strives for metrics other than just accuracy. I think important metrics are accuracy per joule or accuracy per latency. There are a few things that keep coming back, something like depth-wise separable convolutions. The memory pattern there just doesn't lean itself very much to acceleration. So it's highly likely that the community will land on some middle ground. Now, finally, we do have to acknowledge that this is a system. We're not just talking about one camera or one application. In reality, this is a network of cameras and a network of applications that constantly refresh over time. One observation here is that pure ML per frame inference is quite noisy, and doing it on every frame is actually quite expensive in terms of resources. So you could ground your inferences in time by leveraging temporal coherence. But on top of that, you also have occlusion, which means that you need to use multiple cameras for a single problem. So you could bootstrap your inference together, correlate them, and force temporal coherence, and then you have a full stack application. Obviously, there's no room for a per camera application. So frames have to be reused over multiple applications, which begs the question whether you can unify applications into a single model or a single model head. One important aspect that is quite unique to AR/VR, I would say, is that these cameras have a fixed relationship to one another. They are essentially a rigid body with fixed correlation. And once you realize that, there are a lot of shortcuts and tricks that you can play to establish the camera-to-camera correspondence and essentially accelerate your applications. Moving on to the system architecture, but before I go, are there any burning questions that I can answer, Ravi?
Yeah, actually, there were a few questions in the Q&A. One of the most popular ones is asking about what would be the max resolution or frame rate that is acceptable for a common tiny platform, for example, like a Cortex-M4 processor. Could you comment on that?
Yeah, it heavily depends on the application, I would say. So on the camera side, we have cameras that allow frame rates up to 100 frames per second. I would say that's a fair trade-off there. For a low-power microcontroller system, if you can keep the memory footprint and the operations quite low, I would say we could get to order of magnitude 10 frames per second. But any faster than that and any bigger model than that, you would have to go to a more heavy compute enabled hardware system.
Okay, thank you.
So finally, talking a bit about the system architecture to enable all of these applications. Like I said, I think we can conclude from the first part of my talk that it's not just about machine learning acceleration. The problem is a marriage of pre and post processing, learned computer vision, and algorithmic computer vision. So the question that we are trying to answer today in research is essentially how do you architect a system that efficiently executes these applications? KPIs being energy, latency, and again, energy. It what makes or breaks everything. So in this huge space of applications that you can think about in AR, will be a huge challenge to enable them within real world constraints. I like to think of the system as a multi-tier system. It typically starts with an image sensor, is augmented by a first layer of sensor-specific processing, communicates those results over a wired link to a more central processing unit, which then relies on a much bigger processing unit somewhere remote with an entirely different spectrum of energy constraints and data availability. Now, for each level of processing, you can split up your application and how many computations are handled, what the actual computational efficiency is of that operator in that layer, and how much energy that would cost. An equally important part is the inter-tier communication, which you could think of in terms of bits to transfer, energy per bit transferred, and how effective compression is, or how well the previous processing layer was able to compact the data. And this then applies to each of these layers. Now, obviously, this is an optimization problem with many moving parts, maybe too many to handle in one go. So I would say the key takeaways are for sure that your energy budget and your latency are proportional to where you are in the system. Computer vision is not a very effective way of compressing data if you think about it. If you think what the data compression is that you get per op, typical compression algorithms do a lot better. Next, the computational efficiency that you get is as much a function of the architecture as the actual technology node that you land on. So one typical thing we see is that CMOS technology for image sensors kind of prevents you from having having very good computational efficiency this close on the edge. Now, machine learning replaces a lot of the computational graph by essentially weights or coefficients, and retaining those in memory is quite a challenge because they have to persist over a period of a single frame or even indefinite. So memory retention is a big issue there. You also can't undervalue the interconnect. You have to communicate a lot of data. And finally, you can omit a lot of the overhead by carefully scheduling your workload across this system. Make sure that you have an efficient power on and power off mechanism. Now, finally, to create some context, and I put some numbers to these considerations. So if you look at an application at 30 frames per second, running at 8 bits per pixel for a VGA camera, it's not unfair to say that that camera would use 50 milliwatts at 30 frames per second if we think about all the camera specs that I brought up earlier. Machine learning inference nowadays, people are looking at teraops per watt. So middle ground is 1 teraops per watt, I would say. And for 10 megaops, that would amount to, let's say, 10 microjoules per frame. And immediately we observe that this is quite smaller than what our camera would consume per frame. Then we have to retain this model. Let's assume a 1 megabyte model that has to persist over a single frame with some leakage attribute to it. So that would bring us to 26 microjoules per frame. Again, bigger than the actual computer vision part. And then we have to communicate data. That will depend on how efficient that channel is, a wireless channel versus a wired channel. Communicating full frames versus just the inference results will make a big impact here. I would say the key takeaway here is that the system optimization is not just about ML, but it's also about all the other blocks that interact with it. And there's a lot of things that I did in my previous research, technology knobs and even architecture knobs that are very powerful. Dynamic voltage and frequency scaling, putting everything close to the edge. But these don't work for all of these components. It's a lot less graceful when you apply these techniques to something like a sensor or even an interconnect. Now, I won't go into the detail here, but keep in mind that there exist other sensors, especially IMUs, are really powerful to augment your visual data. That is when you can use them on the device itself. So sensor fusion is a nice feature here. Finally, some words about what would be next. Like I said, image sensor technology is currently preventing us from really driving down that sensor power. So an advanced technology node there would be quite handy. On the other hand, compute technology and architecture innovation are going strong still, that obviously thanks to the large community that is working hard on this. And we also see that there are emerging memory technologies being introduced that have significantly better retention properties. This provides good opportunities for large and embedded memory. And then last, 3D stacking is something to look out for that could essentially bring all of this together into a single silicon stack. Now on the machine perception side, we do see a need for multi-sensor and multi-application models. And we do have to recognize that you will never get 720-degree field of view, full HD streaming from something like a headset. The power is just not there. So other solutions have to be looked for, and then we realize that there's a lot of redundancy in the visual information that we capture. We sample a first-person view at 30 frames per second, but none of the pixels actually change. So thinking about a more holistic approach that targets task-critical information gathering rather than full information gathering is something to look for, especially when you can ground it in something like a real-world index. This could be very powerful. I think that brings me to the end of my talk, and I'll be happy to answer some more questions.
Thank you, Hans. That was an excellent presentation. I really like the fact that you emphasized on the system design, and that's something that most people, generally when people are solving narrower problems, they don't look at the entire end-to-end power. System design, you get the best if you look at the whole thing. So thank you for emphasizing that, and especially on the image sensor design. That is something that we're seeing some new interesting developments coming up, especially towards the lower power. But you're right. I think there's a lot of scope there. And along those lines, there was a question about, do you see a continued role for the image sensor processor to clean up the sensor data before ML, or do you think that the role of the ISP can be kind of integrated into, let's say, the early layers of an ML pipeline?
Yeah, that's a good question. Like I said, there's indication that ML can be trained to be tolerant for these things. On the other hand, maybe I'm a bit on the conservative side, but a lot of these non-idealities do have known sources, which means that we could model them pretty well, and we have a pretty good idea of how they impact image quality and what the result of that is. So I think enabling correction there, especially for low-hanging fruit like dead pixels or lens shading or any of those things, I do see a continued role for more traditional CV. Typically, those are handled in hardened data paths, so they are also not of the type of overhead that you would get by running them on a more generalized compute system.
That makes sense. We were talking about what parts happen on the edge and what parts get transmitted to the cloud processing. What would you say is currently the split between how much of computation number crunching happens on the edge and on the cloud?
Yeah, I think we want to get as much as to the edge as possible, and the key metric there is latency, right? All the latency critical use cases are or have to be enabled at the edge. And for something like a Quest headset, that is essentially everything. But when we really start splitting up those applications across something like an edge device and the cloud, you have to think about the problem that you're solving and the redundancy that is in a lot of the information, right? If you can get away with something like a 1 frame per second inference or even less, data that does not need to be updated as often as possible, the cloud is essentially for free when you think about the edge device there. So apart from the communication that you need to emit it, you could get away with it. And then the consideration becomes you only have to transmit that frame once, and you can run all the applications, essentially distributing the cost of transmitting that frame over all those applications, but then in the cloud. Yeah.
Absolutely. Makes sense. Another question that's quite popular is what type of CPUs and accelerators are being used in the proposed VR system? And can you give some specs like their frequency, RAM, and other resources?
I can't go into too much detail there, but the VR devices that we have today on the market run on the hardware that you find in any mobile system or smartphones today. I'm sure there are tech breakdowns on the internet that you can find, but VR is currently not the biggest consumer market, I would say. It's definitely ramping up. So we do rely on a lot of the hardware that the mobile community is bringing up. When you go to, and that is because this is the first generation, right? For future generations, it will be about enabling VR and AR specific use cases and specific hardware. And then I think it will come down to a lot more customized hardware.
Yeah, I think we're starting to see that trend, making custom hardware for this dedicated task because, yeah, repurposing general purpose things won't necessarily work as well.
Yeah, exactly.
So, we have actually quite a bit of more questions, but in the interest of time, I think we do have to switch to the next speaker. Thank you very much, Hans. I will consolidate these questions after the talk into the forum, and for people who hadn't had a chance to ask questions, please do ask in the forum. Yeah, let's thank our speaker again. Thank you very much.
You're welcome.
And please do feel free to continue the conversation at tinyml.org/forums. We will update the questions that you've already posted here that we haven't been able to answer over there. And we can get our speakers to answer the questions there as well. Once again, I'd like to thank our sponsors, Edge Impulse, and if there are additional sponsorships are available, so please contact Betty at tinyml.org if you or your organization are interested in sponsoring an upcoming talk.